Okay, the empirical gas laws are relations between the gas law variables. Which include pressure, P, volume, V, mass, N, which is moles, and temperature, T. And in the gas laws, you certainly need to remember that for the most part, we'll be using Kelvin temperature, which is degrees C plus 273. So, and I'll show you when we get there the importance of converting your Celsius to Kelvin. Well, the application of the empirical gas laws is to adjust the conditions of the standard equation to non-standard conditions. And that's called an STP conditions, as I've mentioned it a couple of times in the past, from standard conditions to non-standard conditions. Which of course is non-STP condition. Oh, okay. Okay, let me start that phrase over. STP condition starts with pressure, and the first pressure is 1 atmosphere. That's your standard pressure conditions. And it's also 760 millimeters of mercury. There we go. This is called a mercury barometer, as you can read as well as I can, but what is done in the international standard units is that they measure what they call a 1 atmosphere when this is 760 millimeters above a pool of mercury. This is an inverted test tube that's longer than 760 millimeters or 76 centimeters. And so when it's that point, they call it the standard pressure. And when you see in the data millimeters of Hg, that's what it refers to, is how high that column of mercury. So that's why I write this. I can do better with that one. Millimeters of mercury on the end of it. Now you'll see me just write millimeters quite frequently when we're scooting through problems quickly, but that's what it means. Okay. Just a minute. Sorry about this, guys. This is stuff I should have done earlier. Oh, if I do this, it'd probably come into focus very nicely. Just a glitch in the video, but we do what we gotta do. All right, there we go. Ta-da. Okay, volume is based on the molar volume we've talked about in the past. That means that's the volume occupied by 1 mole of any gas. We did not specify a specific volume like 22.4 liters because the conditions have not been specified. If conditions are STP, then molar volume is, for any gas, 22.4 liters per mole. And you recall from earlier lectures that this is the standard for the what we call the standard equation. The standard equation, as you recall, is when you write a chemical formula equation, as it's written, you assume it's at standard conditions, STP conditions. So that's 1 atmosphere and 0 degrees Celsius, yada, yada, yada. And then you can assume 1 mole is 22.4, and if it has a 2 in front of the gas phase, it's 44.8, and so forth. We'll expand that later on. Okay. Well, of course, we talked about 22.4 per mole, so the standard mass is N, and that's the common symbology for the mole is the lowercase n, and N is equal to 1 mole gas. Okay. If I cut that in half, I have to cut the standard volume in half if we're at standard conditions. So if I had a half mole, it'd be 11.2, and if I had 3, it'd be 3 times that, and so forth, just to put that hit that nerve. And then finally, and then temperature. The standard is your Kelvin value. But you want to kind of keep in mind that a Kelvin is equal to degrees C plus 273. And so in each problem that we'll be working with in the gas laws, it's just a no-brainer to convert your temperatures given into Kelvin. Okay? The reason is if one of the gas laws has temperature in the denominator of a ratio, and if you put 0 degrees, that makes the math illegal, so to speak. So we'll show you that as we get deeper. STP, and people will just generally say 0 degrees Celsius and 1 atmosphere. And then, of course, you just remember the 1 mole and molar volume, the mass, and it corresponds to the volume. That's a very important statement, so listen to what I just said. In any of the gas law systems, when you're talking about the variables, mass relates to volume. 1 mole is 22.4. What would 2 moles? It has to be 44.8, right? And then cut it in half is 11.2. So as we go through this, keep in mind that when we're working problems and they have to have mass, you're talking about volume also, those two kind of proportional. So we'll expand on that as we get deeper. So we want to start with 3H2 plus N2 gas. Everything's gas phase in here. I like this reaction because it all has different coefficients on them. And we've talked about what you can calculate from a chemical equation in the last chapter. And that includes moles, equation mass, and gas volumes. Well, particle numbers, I better put that one in there. And I'm going to move down here a little bit, gas volumes. That's the one we're really interested in. So, but to review this very quickly, what do we know from what I've given you here? So you open a problem and you're looking at it or working in the lab with a gas phase reaction. Number one, you might put on a sidebar, solids and liquids don't count in this, so to speak. In other words, they don't have molar volumes. They're zero molar volumes. And so everything we're dealing with is gas phase only. So you'd have some reactions have solids, liquids, and gases all inside that equation. Well, if you're working gas law problems, you'd only focus on the gas phase component. So anyway, what do we assume this to be? This is as written. This is at STP conditions. We don't have to have it told to us. We don't have to have it written in the margin of the problem or anything else. So once the problem is given to you, just the equation by itself, it starts at STP. Now the reason is we have to have a starting place because you work a problem at STP and then if it wants it in something different, you adjust using the empirical gas laws. And that's what I'm trying to show you how to deal with here. So kind of focus on that. So I'll say it again. You given a problem, you have a reaction, you assume it's at STP. So you first work the problem at STP, and then you reach over and you pull over the formula you need for the gas law adjustment. So you have temperature moves up to 25 degrees. So that's going to give you different volumes and stuff. So that's what I'm trying to show you. We have a place to start at STP, calculating pressure, volume, temperature, mass. And then we move to non-standard conditions and use the gas laws to make those adjustments. So keep that in mind as we move through this so you'll understand what I'm trying to, because it gets very busy in numbers and equations and stuff. Well, we remember this is 3 moles, 1 mole, 2 moles, right? And equations, this is 3 formula weights, 1 formula weight, and 2 formula weights. And then particle numbers is 3 Avogadro's number, 1 Avogadro's number, and 2 Avogadro's. This is what we covered in the last chapter. Everybody good on this? All right. Now, the reactions, the numbers in here represent reaction ratios. And they're always calculated by ratio and proportion in pairs. So 3 will always use 1. What if you had a half? How much would it, it would use, if you half of the 3, divide by 2, this would you have to divide by 2 on that one also. And so it's proportional up or proportional down. Well, the same thing goes down here with gas volumes, except we use what we call the standard molar volume. Well, not standard, just the molar volume. So this is the volume occupied by 1 mole of gas. Now, without defining conditions, we simply say this is 3 molar volumes, 1 molar volume, and 2 molar volumes. And at STP, you can 1 VM equals 22.4 liters. That's what I've been telling you. So we can fill in this. Therefore, we have 3 times 22.4 liters here, 1 times 22.4 liters, and then 2 times 22.4 liters. So that's pretty straightforward, right? And as far as the total volume, you cut it in half. Of course, you got to cut the volume in half and so forth, multiples and what have you. Well, This row, of course, is at STP. Now, the essence of the work that we're about to do is is the volume or pressure at non-STP conditions. That is the big question, because you'll work the problem first in STP terms, and then it might ask, what's the volume if you change the temperature and pressure to this, that, and other? That's the whole point of applying the empirical gas laws. And so that's what we want to show you now. So we want to start with a simple problem. When you look at this problem, you need to, what volume can be produced at 25 degrees given, let's say we assume 26.5 grams of N2 gas in excess H2 gas. So we want to start this, and we want to convert data to moles. So given in this, I'm going to redo the equation. And we're given 26.5 grams of, did I say nitrogen? I'm sorry. 26.5 grams of nitrogen, and this will be in excess. Okay, nitrogen's 1428 grams per mole. Everybody good? And so if we get 0.946, how many moles of NH3 will be produced? Well, the number's smaller, right? I mean larger, my bad. So you want to use, this has understood to be a 1 in front of the nitrogen, yes? So would you multiply this number by 1/2, or would you multiply it by 2/1?
2/1.
No, of course. So this would then be 2/1, which takes advantage of the coefficients balance equation, and to achieve a larger number from what you have. Okay, so we're going to multiply that by 2, and so we get 1.8. Well, yeah, that's actually 1.89 mole in H3 gas. Is everybody good with me so far? Any questions? I need you to keep up right here. Very important. Okay, so here we are at 1.89 moles. Well, what it wants to know in the problem is what volume at those conditions. Well, the issue is you must start at STP and convert to non-STP. Well, at STP, we know we have 3 molar volumes of H2 gas. We know we have 1 molar volume in the equation of N2 gas and 2 Vm NH3 gas. So at STP of molar volume is 22.4 liters. So our answer at STP is 2 times 22.4 liters. And of course that is 44.8 liters at 0 degrees Celsius and 1 atmosphere. So you didn't have to really do a lot of deductive process to work with the standard equation. But the problem is not asking us for standard volume generated. It's a non-standard volume. Now what happens if you heat a gas? Does the volume go up or go down? Goes up. And this is kind of an intuitive thing all students seem to understand. So heating a gas, volume increases. So we go V1 to V2 at T1 going to T2 is what we're talking about. So if we increase, we go 0 degrees Celsius to 25 degrees Celsius, we can expect V2 to be greater than V1. Therefore, V2 is greater than V1 because it's going to expand. Well, we know what the volume is at standard conditions, 44.8. So we're looking for a number bigger than 44.8. Yes? Okay. Bring that on up here. When we talk about volume of a gas at as a result of changing temperatures, we're talking about what we call Charles' law. And it's a volume temperature relationship. And when we deal with that, pressure and mass are constant, unchanged. So what we can do is to illustrate the derivation of the empirical formula is start with a piston cylinder with a piston, and it'll have volume of gas in here at, well, let's say V1, and at temperature 1. Volume 1 at temperature 1. So now we want to heat gas. Now cooling would be the same concept, but of course it would go down in volume. So the outcome of this would be expansion. To temperature 2, which is warmer than temperature 1, and of course volume 2 would be larger than volume 1. Okay, now what we need to do from a mathematical standpoint is say, okay, we increase temperature from here, increase temperature to here. Then what's going to happen to volume? Will it increase or decrease as you go from first case to case 2? Well, I could say 1 to 2, 1 to 2, case 1, case 2. So we already see from the empirical relationship, the experimental relationship, the gas is going to expand. It's going to have a larger volume. So we increase temperature, increase volume. Yes? Now, there's no big mystery here. So this is called a direct proportionality or direct relationship. Okay, so what we have is volume as a function of temperature, we say volume is directly proportional to temperature, like that. So it increases. Now, if it's an inverse, it'd be 1 over the second term. So now, to make an equation out of a proportionality, we always put in what we call a proportionality constant. The proportionality constant just equates the two sides, and it's always the same for the case 1 temperature volume and temperature 2 volume temperature. So this goes here, we insert and set equal at K times T, like that. And then we can solve this for K to equal volume over temperature. Everybody good? This just says the experimental results is direct. We want to equate the two variables, and that's volume equals KT, and solve for K. Now, K1, case 1, will always equal to case 2. Always. Now, we don't care what the number is. We just know it's the same. Because if this is true, then we have V1 for K1 over T1 equals V2 over T2, like that. Straight out. This is the empirical Charles law formula. Okay, so now with this, we can go back and answer our question. Now, what I tell students in this context is that you make you a data table. So let's repeat some of the data we have. 3H2 plus, and it's all gas. Well, I better put it in there. I'm getting in a hurry. Wait a minute. Let me clean this up. Okay, so we already know what our volumes are. Volumes are 2 molar volumes. And at STP, I'm going to write it right. This would equal 2 times 22.4 liters, which is equal to 44.8 liters. So volume at STP is that. Okay, and at STP, we're talking about 0 degrees Celsius. All right? Now, it's interested in changing this to volume at non-STP, which is 25 degrees Celsius. What would the volume be? Like that. So we want to look at V1 over T1 equals V2 over T2. And so by substituting, we have V1 is 44.8 liters over T1, which is 0 degrees Celsius, which is equal to V2 is unknown. Temperature 2 is 25 degrees Celsius. So based on the data that's given, that's what you would throw into the formula. However, this is a problem, as you probably already know. You can't divide by 0. And so I'm trying to make a point here that, yeah, it's always, temperature is always converted to the Kelvin value. Just move this up here. So 0 degrees Celsius would equal 273 Kelvin, and this one would equal 273 plus 25, or 298 Kelvin, like that. And so this would be, of course, our unknown, and so now we solve for the question mark. So liters of ammonia at 25 degrees C and well, at 25 degrees C, let's stop right there, 25 degrees is equal to solve this expression right here. Okay, so it'd be 25 degree, I'm fixing to mess up, 298 Kelvin times 44.8 liters divided by 273 Kelvin. And so that drops out. Of course, using Charles' law empirical formula relationship, where V1 and T1 are really from the standard equation. And so temperature is 0 Celsius or 273, and the volume is based on 22.4. So you have this already. This is your starting point. That's why I gave you that in the initial part of the lecture. And you're going to the non-STP conditions, which is V2 and T2. And you use the expression here to get the relationship. Everybody good? I mean, it's just taking the data that's given and put it in there. Now, the other point that and we got this number, but the calculation is still at 1 atmosphere, and that's not what the problem asks for. So we have to take into account the pressure effect. Now, the point I'm trying to make here is that we focused on the temperature adjustment, disregarded the pressure. Well, that's legal in this. You make an adjustment on pressure, and I'll show you a shortcut in just a minute. And then, once you finish that, you adjust the pressure. And so I want to develop the next empirical law called Boyle's law around that, and we'll adjust the pressure from wherever. The volume will be adjusted to non-standard volume based on pressure this time. Okay. So again, we're given and what we know now is that at standard conditions, we have 3 molar volumes, 1 molar volume, and reacting with 2 molar volumes, and that's 2 times 22.4 liters, which is 44.8 liters. So we're adjusting this from a volume 1 to a volume 2. So trying to keep things in perspective on the problem. Now, we're going to calculate the pressure adjustment. And the pressure adjustment, we're starting out at STP. Pressure is equal to 1 atmosphere, and that's equal to 760 millimeters of mercury. And that's P1. P2 is non-STP, which is equal to, well, we gave it in millimeters, 735 millimeters of mercury. So we're going from 760 from P1, which equals 760 millimeters, to P2, see I'm dropping the HG, save me time, to equal 735 millimeters. Okay, so in this process, we're decreasing pressure. So what has to happen to volume? Anybody know that one? Okay, you probably need a diagram. Okay, so in graphic standards from case 1 to case 2, we'll start out with our gas and a piston cylinder. This is pressure 1 at volume 1. Okay, now you want to go to pressure 2, case 1, case 2. You want to make this a decreasing pressure. All right, now squeezing the balloon. You push a balloon, think of it. Squeeze the balloon, well, the pressure goes which way? Up. That makes sense? Okay, but what happened to the volume? It went down, didn't it? It went opposite. Okay, so that's an inverse relationship. So what happens is when we increase pressure, we have to make a lower volume. But the problem that we're decreasing pressure, so it's opposite. So we want to pull the volume up. So it goes to a higher volume. To pressure 2. So pressure 2 is less than pressure 1 with volume 2 greater than volume 1. So you are increasing volume, decreasing pressure. It's expanding the gas, so the particles aren't as close together and bumping around. But if you push the piston down, decreasing volume will squeeze the particles closer together and the pressure goes up. This is again an inverse relationship. Well, we write an inverse relationship for pressure as a function of changing volume becomes pressure proportional to 1 over V, and we apply the same math techniques. We put in a K value for 1 over V and solve for K, which is pressure times volume. And case 1 is where P1 V1 equals now, well, let's write it K1 equals K2. Therefore, we put in the PV, PV1 equal PV and 2 and 2. And this is the empirical form of Boyle's law. So working just with that expression, P1 V1 equals P2 V2, we can now predict what the new volume would be based on going from 735 to 760 to 735. And we know that pressure is proportional to 1 over V, and ultimately this gives you P1 V1 equals P2 V2. And so we see that P1 is 760 millimeters of mercury. Volume 1 is 44.8 liters, and that's equal to pressure 2, 735 millimeters, times volume 2, which is the unknown. And so solving for V2, 760 millimeters. Millimeters drop out. Go back me up on this now. Make sure I'm not lying to you. So we've worked the problem using a temperature adjustment and then separately, and then we worked separately a problem as a function of pressure. Well, the other two relationships are known as Gay-Lussac law and Avogadro's law. And so I'm just going to set up and finish those, and then I'm going to go into the empirical combined law. And then once you see that, you won't have to remember all these little individual details. Everything, you just remember the combined law, you can do any of them. Okay, the Gay-Lussac law is gas in a box, is what we call it. So it's a constant volume, constant mass. So that is pressure proportional to temperature, and the way we use it is constant mass and constant volume. So the subscripts indicate constant gas in a box. So if you have a gas in a box and it's pressure 1, and you go to a gas in a box, pressure 2, by heating, so temperature 1, temperature 2, heating, what will pressure 2 do? Increase, right? I mean, everybody knows that, I think. Okay, so it's like heating a confined pressure cooker. Heat the gas, the pressure goes up. So pressure is directly proportional to temperature, which gives pressure to equal, and we put in our proportionality constant, then solve for the proportionality constant, and that's pressure over temperature. Well, K1 always equals K2, and this gives the empirical gas law form of Gay-Lussac. P1 over T1 equals P2 over T2. Like that. Then the last one will be Avogadro's law. And this one is a mass-volume relationship with pressure-temperature constant. So volume is directly proportional to mass, like blowing up a balloon, and a function of mass at, trying to rush, at a constant pressure and temperature. So this is blowing up a balloon. Now that's pretty easy to visualize. What do you do when you blow air in? You're increasing the mass, right? So what's the outcome? Balloon gets bigger. So this is a direct relationship. Volume is directly proportional to mass. Usually they'll list it in moles. And of course that includes the proportionality constant. And we solve for K. And so K equals V over mass. And for case 1, case 2, K1 equals K2, then V1 over mass 1 equals V2 over mass 2, like that. And so this is the empirical formula for the Avogadro's law. Well, if you wrote these laws down and put them, you'd have Boyle's law. This is the way it usually starts. Charles' law, Gay-Lussac, and Avogadro's. So the proportional relationship is pressure proportional to 1 over, or volume and pressure. Let's go volume on all. Volume proportional to 1 over pressure. So this is an inverse relationship. And this leads to the empirical relationship, P1 V1 equals P2 V2. Pretty straight. Okay, Charles' law is volume directly proportional to temperature, and this leads to a relationship V1 over T1 equals V2 over T2. Gay-Lussac is pressure proportional to temperature, and the other two variables constant. So that's a P1 over T1 equals P2 over T2. And then finally Avogadro's is volume proportional to mass, like this, and so that's a V1 over N1 equals V2 over T2, like this. Well, without going into an overdeveloped explanation of what this is, I can combine all these into one equation. And it's called the combined gas law. Case 1, case 2. And I could solve for K, take those K values and say, well, K is this, and then move them all together. But it ultimately comes down to case 1 equals case 2 in the following. PV over NT equals PV over NT. And that's the simplicity of this. 1, 1, 1, 1, 2, 2, 2, 2. This is the empirical relationship called the combined law. And most problems come to you with constant mass numbers, so it's PV over T, PV over T. For those that can remember some of this from earlier courses, you might recognize that. Now, you don't have to remember all of the empirical laws. Now, for the next exam, you will need to know the names, that Boyle's law is a pressure-volume relationship, and Charles' temperature-volume thing. But after that, you probably won't be concerned about it. No, I won't make a big issue out of it. But from this, you can define, you don't have to really know what the name relationship is for solving problems now. What you need to do is when you work a problem, you make a table, case 1, going to case 2, and this is what a problem will give you, and we'll work one when we get back from break. P, V, N, and T, P, V, N, and T, and then you just label them 1, 1, 1, 1, 2, 2, 2, and 2. So the problem that comes to you will say a gas at whatever conditions, case 1, is going to case 2, what is the, whatever they're looking for in case 2. So usually it's, say, an unknown volume. So the case 1 data and case 2, except for the unknown, is given. So you'll be given all of everything in here in one form or another, and then you apply it to the combined law. Well, let me show you, and this will save us all, save you just gobs of time. Let's say you're given P1 and V1 and 1, I'll do it this way, T1 and P2, V2, N2, T2. I'll make up something real quick. 730 millimeters, 765 millimeters, 21 liters, unknown, mass 1 mole, temperature 25 degrees C, 25 degrees C. So when you look at this, you want to apply this data. See, I took all 4 variables and made a table. Case 1 and case 2. Okay, now I want to plug them into the P1V1 over N1T1 equals P2V2 over N2T2. Now, when you look at the data, what do you see here? These are the same, right? N1 and N2 and T1 and T2 are the same. Yes? Yes. Everybody say it. Okay, they're going to cancel out if they're the same on both sides, right? What are you left with? Boyle's law. So, all right, let's say you had another one, say, given P1, V1, N1, T1, P2, V2, N2, T2. Okay, we're given 760 millimeters, volume is 13 liters, and they want to calculate something else, 1 mole, and you're going from 25 degrees C to 35 degrees C. What's the new volume in here? So you apply that to PV over NT equals PV over NT. 1, 1, 1, 1, 2, 2, 2, 2. And what does this give you? Well, pressures are equal, so we'll take those out. And mass is equal. We'll take those out. What are you left with? V1 over T1, V2 over T2, and that's Charles' law. So by simply remembering the combined PV over NT, 1 going to PV over NT, 2, just extracting the data. You don't have to know who's who. You just plug it in and you know enough math to cancel out the terms that are the same on both sides. And it leads you immediately to the correct empirical relationship. Well, the same way with Gay-Lussac and Avogadro's. And of course, this would give you the pressure 1 at temperature 1 and pressure 2 at temperature 2, because the other terms will cancel out. And this would give you the N1 over V1 equals N2 over V2, and the other terms would be constant if you set up this little table like that, and you work all of them like that. Now, the only thing you have to remember is you can't work Charles' law in Celsius, so that's why I put T on the bottom, because I just 273, 8, 7, 8, 9, 10, 308 Kelvin, and 298 Kelvin. So I'll plug those numbers in. Everybody see my patterns here and stuff? Okay, I want to come back and move on to the ideal gas law, I think. I'll think about it. Okay, and I put a little note over here, but the sidebar that I'm going to use. Okay, so you're going to apply to this, and we already know that this is constant. And what does it want to know? It wants to know V2. And so we solve for V2, which is P1V1 T2 over T1 P2, like that, yeah? And plug in the numbers and you get an answer. Okay, and it's a volume. You good? You okay with that? You should. What it means is that you're given a bunch of data. You set it up with this relationships, PV/NT, PV/NT. Write that down and plug in the numbers, and you get a number. So we'll do that. V2 equals P1, which is 350 millimeters. V1 is 2.75 liters. What was I looking for next? T2 is 400. We want to go to Kelvin, so I'll put that in 673 Kelvin, and 273 goes to 473 Kelvin. So I want to use 673 Kelvin there, and underline all of that. And then I'm going to look for T1, so I'll come up here to 473 Kelvin. And P2 is 400 millimeters. So I can go through and cancel temperature and pressure, and the only unit left is in, of course, liters. And so I get 3.42 liters. Pretty straight in solving that. Everybody follow me on that? Well, there's in my humble opinion, a simpler way even than this to do this. And problems where you list out all of the variables and everything's changing, or maybe just the mass is missing, which is usually the case. What are you trying to do? You're trying to go from V1 to V2, and the changes that occur are calculated individually. Remember how I developed the Boyle's law and Charles' law notations in here? I worked the temperature volume relationship and I ignored pressure. When I finished that one, then I worked the pressure volume relationship, the Boyle's law, and developed it. Everybody remember that? Okay, well, I'm going to do the same thing here. So what's the objective of the problem? Well, of course, it's V2. So I'm going to put V2 right here. And that's going to be related to V1 right there. Well, and it just happens to be 2.75. Now, I'm going to have a temperature and a pressure ratio that will change volume. I'll say that again. I want a temperature ratio and a a pressure ratio that will increase or decrease the volume relative to what's happening in the data. Okay, so when we look, let's do the temperature first, because that's what I did in the notes in the beginning of class. I'm going from T1 to T2, 200 to 400. What's temperature doing? Increasing or decreasing? All right, what happens to volume if you increase temperature? It gets bigger. So you want to use 673 and 473 to make a ratio that will make V1 bigger. Would you use 473 over 673 or 673 over 473? Obvious. 673 over 473, yeah? No big mystery. Okay, that's what you'll do. 473, excuse me, 6, get my act together. Yeah. Okay, I'm through with temperature. We've made our adjustment to the volume relative to temperature. Now we want to make the adjustment relative to pressure. So what's happening in here? We're going from 350 to 400. We're increasing pressure. So what's happening? Notice what I've written over here. The only inverse relationship in the empirical laws is Boyle's law. All the Charles, Gay-Lussac, and Avogadro's are all direct relationships. So if you're working with pressure volume, this is an increasing pressure. This is ultimately going to use a decreasing volume. So you need a pressure ratio that will decrease that volume. And so would that be 400 over 350 or 350 over 400? That's the question you ask yourself. And obviously it's 400 millimeters over 350 millimeters. Millimeters drop out. All I need is the 2.75 liters here. I think, yeah, right there. And you check it, and it's 3.42 liters at the end of it. So if you set this up and just simply look at, well, I'm at V1, I need to change it to V2. Well, first I'll change the temperature, see what the temperature's doing, set up a ratio and multiply it in, and pressure, multiply it in. And that beats memorizing all of the laws and all the details that I've just given you. Okay? Now, for the next exam, I will ask individual questions about, well, Boyle's law will deal with what, and Charles' law and so forth, like that. That's kind of part of the learning curve. But as you move into the next sections and chapters that are kind of generic in nature, you will have a pressure-volume relationship. You'll know that it's an inverse, and you just use it by simply using the ratio to adjust any volumes that you might have, and through a sense of what's going on in this. The next section is referred to as the ideal gas law. You probably recognize this as PV equals nRT. The ideal gas law comes from the combined gas law, where you're changing a reaction conditions standard to non-standard conditions. So you can say this is based upon combined gas law with changes from STP conditions, the standard equation, to non-STP conditions of pressure, volume, temperature. Well, mass is non-standard is equal to mass and standard. It's considered a solid effect. So you're really changing only the PV and T. So that's the essence of this. So what this says is you have P1 V1 over N1 T1 going to P2 V2 over N2 T2. Yeah? Case 1, case 2 scenario, right? No sweat. Well, this one over here is standard STP conditions, And this one is, of course, non-STP conditions. Right here. Well, for all equations at STP, now we want it in the SI system. Now watch what I do here. This, if you've never seen this before, it will be a revelation if you studied this before. P, V, N, and T, standard, 1, 1, 1, 1. That's our standard conditions. What's the standard pressure? 1 atmosphere in SI. What's the standard volume given that we're talking about 1 mole at STP? 22.4. And the temperature is 0 degrees Celsius, but we have to be in 273 Kelvin. So case 1 here is P1V, make it cleaner, P1V1 over N1T1. Making a mess, hang on. P1V1 over N1T1. Pressure is 1 atmosphere times volume 22.4 liters, but we have to specify, remember I said volume and mass are interrelated. 1 mole. Now I could also put half mole, but I'd have to cut this in half. But I want to use 1 mole because that's the designated accepted standard. And what was the last? Temperature, 273 Kelvin. Well, what this gives us, can everybody see this? I want to keep it all on one page. Yeah. What this gives us is 0.08206 liter atmospheres over mole Kelvin. Now, if you check, you can change the volume and mass, but if you say cut the volume in half, the moles in half, you'd have to cut the volume in half. But you still get the same number. If I put 1 atmosphere and 11.2 and a half mole, and in 273, I'd still get 0.08206. This is called the universal gas constant. And is for STP conditions of chemical reactions. And is given the symbol R. We're going to capital R symbology. So when we write now bring it on up here. So if we have P1V1 over N1T1 for the chemical reaction at STP, equals P2T2 over N2, I'll get my brain straight, to like this. This is at non-STP. This one is always R, which equals P2V2 over N2T2, which is non-STP, and this of course translates to the standard PV equals nRT. Well, this R is your STP conditions that we just dealt with right here. For any equation, because remember what I said at the start of the lecture, you have to have a starting point, and it's assumed that the equation is at STP. Okay, so you can work all the problems that you want to, assuming that 1 mole equals 22.4 liters. But they're not always at the same conditions. So we have to have a way to adjust. So that's what we just finished showing you. But in using this, you will always get the same number for R, 0.08206 liter atmospheres, mole. It just gets repetitive. And so these are the problem objectives, and in reaction problems. Because what they're going to give you is, they'll say a reaction is run at such and such a pressure, producing so much volume, and you're given so many mass and temperature, and one of those is going to be an unknown. And you're calculating the non-standard conditions because R is at STP already, and you've already calculated that. So you don't, that's what the ideal gas law does. It eliminates that part of the reaction problem. You don't have to go over there and calculate the case 1 conditions. It's already going to come out 0.08206, so why not put that in every time? Okay, we'll do it that way. Given magnesium solid and a couple of hydrochloric acids, aqueous, and that's going to magnesium chloride, aqueous, and let's see, hydrogen gas, molecular hydrogen gas. All right, let's say we start off with 0.4612 grams of magnesium in an excess of HCl, and we want to know what volume of hydrogen gas is going to be generated at, say, 35 degrees C and 780 millimeters of mercury pressure. So that's what we want to, that's the problem given. All right, and you'll also be given R to equal 0.08206. This is posted on the reference sheet at the back of the liter, atmospheres over mole, Kelvin, like that. So, given that kind of problem, you see it's a reaction. Okay, use the ideal gas law. Now, you can use the combined law and do the calculations, PV over T1, it's still going to come out 0.08206 on the left side of the PV over T. Okay? So we use PV equals nRT, and this is the objective of the problem. And that's the non-standard, non-STP volume. And so all we have to do is plug in the variables. Now this is moles of H2 gas. It's not moles of magnesium. You have to, it will turn out to be equal because it's a 1-to-1, but you see what I'm saying? The PV equals nRT applies to what the target gas is. Magnesium is not a gas to start with. What can I say? Okay, so recognizing that, what do we need in here? Well, I need a pressure. Oh, the units must conform to the R value. So if we have in P, V, N, and T, all right, pressure is given as 780 millimeters. Well, atmospheres is the R value, so I have to divide by 760. 1 atmosphere equals 760, so that's it's all posted on your reference sheet. It'll be, all you got to do is look it up and convert to atmospheres. So 780 millimeters divided by 760 millimeters per atmosphere. I have 1.026. Okay, that's the conditions and pressure. Okay, the volume that we're looking for is, of course, your unknown. The temperature is 35 degrees. We'll do that one first. 35 degrees Celsius plus 273, 5, 6, 7, 8, 7, 8, 9, 10, 308 Kelvin. So we want this number into the PV equals nRT. We want this number in PV nRT. And so what is the mass? Now that's the mass of hydrogen from this reaction. So we're looking at magnesium plus 2HCl going to magnesium chloride plus H2 gas. We need moles of H2 gas. So if we have 0.08206 0.4612 grams over 24 grams per mole. You get that off the periodic table. What does that work out to be? 24.3, okay. 4612 divided by 24. I get 0.0192 mole, 0.0192 mole 8 magnesium used to produce 0.0192 mole H2 gas, because it's a 1-to-1 reaction ratio. So once I get the moles of the magnesium, I have the moles of H2. And so this is 0.0192 mole of H2 gas. And so the only unknown here is, of course, the volume. Plug in those numbers and voila, instant new volume. See how that works out. So volume is nRT over P. So we have in here 0.0192 mole, 0.08206 liter atmospheres over mole Kelvin, like that. Temperature is 308 Kelvin. And the pressure is, 780 millimeters divided by 760, 1.026 atmospheres. So you can easily see atmospheres will drop out, Kelvin will drop out, moles drop out, and liters is the only unit left. So that's 0.0192 times 0.08206 times 308 divided by 1.026, I get 0.473 liters of H2 gas for the yield on that particular problem. Now don't get lost in all the numbers here. Okay, what have we tried to show? Okay, what have we talked about today? Okay, we've talked about really the ultimate objective here is how do the empirical gas laws apply to chemical reactions is the ultimate question. And the answer to that question is they're used to convert from standard conditions to non-standard conditions. Now this can be in one of two ways. One, the combined gas law, and two, of course, the ideal gas law. I'm going to put the equations down here. P1V1 over N1T1 equals P2V2 over 2T2. And two, the ideal gas law, where the PV over NT. Let me say this, while I'm trying to relate to equations, and yeah, everything goes back to STP, you will have volumes when neither side are standard, okay? So that kind of thing. So both sides don't really relate to an equation. So, but for equations, PV over NT, 1 is STP, going to PV over NT to non-STP, and this part becomes the R value, which is PV over NT non-STP, and leads to PV equals nRT, which is the same thing as the combined law, except the R value is 0.08206 liter atmospheres over mole Kelvin all the time. So this sign is, that sign's always defined in equation problems. So that will simplify a lot. Now, the only other thing that we talked about was the individual named empirical laws. And so if you write down PV over NT1 data and PV over NT2 data, you'll see what to cancel out of this, and it'll lead to the individual empirical laws that we showed you. So there's a kind of a, while it took me 2 hours to get through all of the details of it, it really boils down to you recognizing just what's on this page as far as their application. Now, experience is always the best policy, so please get into the text. I will make a point of trying to get some worksheets to you, and you work till you understand the concepts. And please ask questions, and if you do that now, you'll find the exam that's coming will be a piece of cake. It really will. There are two specialty problems from the ideal gas law. One is calculation of gas density, and two, calculation of formula weight of a gas based on data given, and you apply the ideal gas law. Okay, so calculation of gas density, it'll be our first challenge here. And so from PV equals nRT, you start there. Now the idea is, well, what is density? Density is mass over volume. So what you want to do in this specialty problem is convert PV equals nRT to an equation that has mass over volume in it, and then solve from MV, M over V ratio. Now you find that you can do that by recognizing what N is. N is moles, which is mass over formula weight. How do you convert grams to formula weight? To moles. You divide by formula weight in grams per mole. So what we'll do is we will take this and convert mass, M, over mole, let's write it out, mass over formula weight times R times T. So I'm just substituting the definition of the conversion from grams to moles. Everybody good? Think about it for a second. See, this you already know. How do you convert grams to moles? Divide by formula weight, right? So I want to substitute that into the N expression, N part of the equation. So you see where I put it in there? Okay, now you want to rearrange this so that you have volume and mass over volume. And then everything on one side of the equation and everything else on the other side of the equation. So how do we do that? Well, I want to keep mass on the right side of the equal sign. Well, I'll move it down here. So I want to keep mass on the right side, and I want to put volume over here, so I divide both sides by volume. So I have volume over here. Well, that's going to be density anyway. And everything else goes to the other side, and that's your formula. Okay, so I have PV over here already. And so multiply both sides by formula weight and divide by R and T. And so there's your formula. PF, I don't need. PF over RT, I'm missing something. Shouldn't be. Oh, I put the volume on the other side, duh. See, this has already gone to the other side. Yeah, so it's P formula weight over RT. That's kind of. Okay, so if you have a problem, this is in that they ask you to, well, what's the gas density at 25 degrees Celsius? So we'll do that. Calculate density of CO2 gas at 25 degrees C. 1 atmosphere. Okay, formula weight's the only thing we need. So what's that? 16, 32, 42, 44. So you got temperature, pressure, and mass. So our density is P formula weight over RT. Pressure is 1 atmosphere. Formula weight's 44 grams per mole. 0.08206 liter atmospheres, mole Kelvin. Temperature 25, that's 298 Kelvin. And atmospheres, Kelvin, and moles go away, grams per liter. That's your density number. Okay, I got 1.8, so you check me on that if you would. Sure. Okay, formula weight of a gas from the ideal gas law. This one's much easier than the density thing. So we start with PV equals nRT. We do the same thing, substitute mass over formula weight, RT. Well, that's the objective. Right there, just solve for formula weight. And so this will give you formula weight is equal to mass in grams times R times T over pressure in atmospheres times volume. It has to be in liters. Because remember, in these kind of problems, when you're using ideal gas law, the units need to conform to the R value, where R equals 0.08206 liter atmospheres over mole Kelvin. Okay, so we recall that PV equals nRT, which equals mass over formula weight, RT. Solving for formula weight is M mass RT over PV. Well, the mass is given as 0.548 gram. R is 0.08206 liter atmospheres mole Kelvin. T is given to be 100 degrees C plus 273 equals 373 Kelvin. Pressure is 755 millimeters. Y'all remember how to convert? Divide by 760. and I just get in the habit of doing it by ATM. And what's it? Volume is 237 milliliters and has to be in liters to conform to the R value units, 0.237 liters. And let me get the pressure number. And this is 0.993 atmospheres. That's good enough. Like that. Okay, so in substituting, the formula weight now is mass 0.548 grams, R 0.08206. Kelvin. Temperature is 373 Kelvin. Pressure is 0.993 atmospheres, so it's just more of a plug and chug kind of problem, and 0.237 liters. So we have Kelvin dropping out, liters dropping out, atmospheres, and we're left in grams per mole, which is the formula weight. And so that would be 71.3 grams per mole is what I'm calculating. Okay. Okay, like I indicated, we have two kinds of problems you will see. Now, these are, when I say specialty problems, you know, what I just worked is what you're going to see on the, what you see is what you get. And so on the exam, so it's a matter of knowing what the formulas are for each one of the calculations. Especially one is density of a gas, and the second one, of course, is the formula weight of a gas at specified conditions. Same way at specific conditions. So that's what the essence of each problem is. For a density problem, density equals P times formula weight over RT. Okay. Now the derivation of the equation, of course, surrounds the N equals mass over formula weight. You substitute that into the N portion of the ideal gas law, and then the formula weight is M as mass in grams, RT in Kelvin, of course, and divided by pressure times volume. Now, these are gimmies, literally, because I give one on each on exam day, and all you have to do is essentially remember the formulas, plug and chug. The only issue is be sure to make your conversions of units to match that of the R value. Liter, atmospheres over mole, and Kelvin.